I would like to welcome all of you to this ESE talk on endocrine disrupting chemicals, part 2. For those of you who weren't here yesterday for the part 1, we then had a general introduction to endocrine disrupting chemicals. And from the perspective of metabolic disease and obesity, reproductive health, and child health. Tonight, the focus of the presentations will be on one specific family of chemicals, the para- and polyfluoroalkyl substances, or PFAS, as we say for short. My name is Anna Marie Anderson. I'm a biologist and senior researcher at the Department of Growth and Reproduction at Rigshospitalet in Copenhagen. My research area is reproductive endocrinology, with focus also on the impact of environmental factors on sex differentiation, sex development, and reproductive health. For the topic tonight, the PFASs, these are a large group of man-made chemicals that have had a broad use for several decades already. They were early on identified as problematic chemicals, mainly because they are very persistent in the environment. They are also being called the forever chemicals. And more recently, the concern about PFASs has increased as more and more reports on exposure hotspots around Europe emerges. And also human biomonitoring studies showing that there is a widespread exposure to PFASs in the general population. And finally, increasing numbers of studies, both in humans and in animal models, showing adverse health effects are related to PFAS exposure. Some of the most commonly used PFASs, including PFAS, are already included in the International Stockholm Convention on the Persistent Organic Pollutants, or POPs. PFAS was restricted in EU for more than 20 years ago under the EU POP regulation, and PFOA has been banned under the POP regulation since 2020. And also for other individual PFASs has there been, and there are considerations for regulation or bans in the EU. But the problem is that the family of PFASs consists of thousands of individual different chemicals, the majority of which share the very persistency in the environment, but for several of them, we don't really have enough data to say anything about the health, potential health effects or environmental effects even. And of course, if we should evaluate and consider regulation for each individual of these PFASs, the time and money spent is really not realistic. So the topic of tonight, ESE talks, is very topical because at the start of this year, 5 EU member states, Germany, Denmark, the Netherlands, Sweden, and Norway, together submitted a proposal for the restriction of a wide range of PFAS uses, including thousands of persistent PFASs. And this is a landmark proposal as it includes a large group of chemicals rather than individual chemicals. And this proposal is now in open consultation and is being evaluated by the European Chemical Agency's scientific committees, and a decision is expected by the end of this year. So with that, I think we should move to tonight's very interesting presentation that I have been looking forward to. And the first one will be by Theodor Halldórsson from the University of Iceland. Theodor is professor in at the School of Health Sciences, and he was also recently involved in the work related to risk assessment of PFASs based on human biomonitoring data in the recently completed EU project, Human Biomonitoring for EU. And the screen is yours.
Great. So I'm supposed to be talking about introduction to PFAS and their adverse health effect, but I think I will follow a little bit on and talk about the properties of these chemicals and what they are before I go to the health effects, because I think understanding that is a little bit important. But per and perfluoroalkyl substances are fluorinated chemicals that have been used, among other things, to produce fluoropolymer coatings, and they have been used as surfactants, and they are found in a variety of consumer and industrial applications. And the reason why they have been so popular and so extensively produced is basically that they are heat, oil, and water resistant. And when you have something like that, there usually should be a red flag that goes up, because chemicals that have these heat, oil, and water, or sort of heat-resistant properties, let alone oil and water resistant at the same time, they do not break down easily in the environment. And unfortunately, which was maybe more difficult to predict in the 50s, was that these compounds bioaccumulate in humans and wildlife. Not all compounds have these bioaccumulative properties, but some of the PFAS have. And what we are measuring in human biomonitoring studies and have been following in humans is basically the end product of a molecule. Either the molecule was used in this way, or it's a degradation product of something, another fluorochemical. And what you have basically with perfluoroalkyl substances is that you have a active sort of hydrophobic carbon-fluorine chain of varying chain length, where the hydrogen atoms have been removed from the carbon chain and the fluorine atoms added, and that requires a lot of energy, and that was sort of, people figured that out in the 50s. And then you have a very strange molecule that basically repels everything. But at the end, you have a functional group, which can be a carboxylate, there can be a phosphate or a sulfonate. And this is what determines the properties of the molecule. It's the chain length combined with the functional group, and the functional group has determined the application of the compound. And what we call long-chain PFAS is it depends on whether it's a carboxylate or a sulfonate, whether that's a 6 or 7 carbon length chain. They should be now largely phased out of production, but they are still frequently detected all around the globe simply because they were produced in such a high volume. And the reason why these long-chain PFASs have long elimination half-life in humans is that the body recognizes them as a short-chain fatty acid, and instead of excreting them, they get reabsorbed by the kidney. And that's the reason why, and depending on the water solubility and the functional group, the varying half-life can vary, but this is basically the mechanism, this reabsorption, which leads to this bioaccumulative property, which is not present in rodents to the same extent. And the sort of lowest energy usually that these compounds can find is to bind with proteins, whether it's albumin or enzymes or anything else, and that leads to some but very unspecific toxicity, I would think. And these long-chain PFAS have been extensively studied. And just to give you an idea, I mean, for example, the PFOA, which was produced by DuPont, it was used as an additive, not the active ingredient in the fluorotelomere production. And that's the fluorotelomere that coats your Teflon pan, but sort of opposite to contrary belief is that you will not get PFOA from a frying pan or these fluorotelomere polymers, but what you will, basically the PFOA was cooked off during the manufacturing process, and what you have is a polymer that should be enough. On the other hand, when we look at other compounds like PFOS, it was used as a backbone of these surfactants that we use to repel water or oil and coated our furniture and raincoats with, and that breaks down more easily or releases more easily. And then the molecule breaks down and you're exposed to the acid. And that explains why the level of this compound have generally been much higher than for PFOA. But then all these compounds find their way into the environment and we get exposed to them. And then we have the short chain PFAS, where we really don't know not much about, and I wouldn't be able to tell you where they are used. They could be breakdown molecules. They could have been used for different properties. But they are more easily excreted via urine because they have the body doesn't recognize them as fatty acid or an energy substrate, and therefore it's excreted. And we haven't really studied them, and we really don't know much about the toxicity. They are just generally assumed to be less toxic. And what you see in human biomonitoring studies is that the level of the long-chain PFAS have been going down in the general population. We barely see the short-chain ones, but what we are seeing now are these hotspots because the dust has settled, and now we're actually seeing where the local contamination is. And of course, there are hundreds of chemicals around. They break down, and they all find their way into the environment. And at some time point, I would think that the new chemicals will emerge, but the newer molecules are designed to be less resistant in the human body. And the And that is basically the dilemma I think we're seeing in Europe and many other places. You can see on the map here, there are the red dots are the known hotspots in Europe. They tend to be where industrial activity is high. The blue ones are probably civilian and military airports around Europe. And basically what we are seeing is that these compounds find their way into the environment. They can contaminate groundwater. They form foams at the upper layer of water and seabed, and then they blow into the surrounding grass by the shores, and they can contaminate animals and so forth. So we are seeing sort of strange behavior and strange properties, and they have been actually quite challenging and fun to study these chemicals. And that brings us to the regulatory context. And the reason why I'm going to talk about that is that I was a member of the EFSA panel who published the 2020 opinion on PFAS. And I mean, in 2008, I think EFSA published the first opinion, and in 2018 and 20, there was an update. And I think it's important to understand the history of it, to understand the toxicity. And in 2020, there was a health-based guidance values established for the sum of 4 long-chain PFASs, the one that we know most about. I think we were asked at the time to do about 35 chemicals, but we only had information about 4 that could lead to something meaningful. And if we look at the first EFSA opinion from 2008, they quickly identified the liver as the primary target organ. The unspecificity of the effect was that they used absolute increase in liver weight as the most sensitive adverse health outcome, and that's a bit strange. I mean, your liver grows if you drink too much alcohol, and of course, for many chemicals, it also enlarges if you feed enough chemicals to animals. But the safe level derived for P4 was around 1,500 nanograms per kilogram body weight. And today we are at a level which is about 1,500 times lower. During that process, when people started to become, or sort of, as year passed and more epidemiological data and toxicological data came, the regulatory agencies still stuck to the same liver weight studies, but they just derived slightly lower health-based guidance values because they knew more about the kinetics, and maybe they used other uncertainty factors that they could play around with and get to a level which was lower but still higher than the background exposed level. That would be my interpretation. Which brings us to the EFSA opinion from 2020. And by that time, we had wealth of human and animal data, and after sort of going through several hundreds of studies covering many endpoints in humans and animals, the opinion identifies 5 what we would call sort of critical or semi-critical likely endpoints of concern that were likely to be causal, and that was, and I'm going to talk briefly about them. Each of these endpoints have their own strengths and weaknesses, but in the end, the latest health-based guidance value was based on immune outcomes or reduced response to vaccination. And for example, if you look at birth weight, I think there are most epidemiological studies show inverse association or slightly lower birth weight with higher internal serum concentrations during pregnancy. The strange thing about these consistent findings is that there is a modest decrease in birth weight, and it is not accompanied by clear associations with low birth weight, which is birth below 2,500 grams or small for gestational age. And there has been some hypothesis that this modest association could be due to confounding due to variation in uptake and excretion of the substance, but overall there was some concern about this outcome, but the effect was considered perhaps too small to be used as the most critical endpoint. The other outcome that had been known for a long time, which is consistent with these sort of increased in liver, is that that most studies, both occupational and conducted in background exposed populations, show slightly higher liver enzymes or serum ALT levels with higher exposure, and you can see it both internally measured in serum, but it has also been noticed that people living in areas where drinking water contamination varies, you can see a dose response on average increase in serum ALT levels in these populations. The effect was considered toxicologically rather small. I'm not so sure about that, but and people found it quite strange that these effects would occur at much higher concentrations in rodents, but I think that's mostly related to the fact that the elimination half-life in rodents and humans is different. But so this was flagged as a critical outcome, but not the most critical outcome. The other effects, which I think was heavily debated, and if you read the EFSA report and corresponding documents, there's a lot of debate about the consistent findings in epidemiological studies showing higher serum cholesterol levels with higher PFOS and PFOA exposure. And you also see the same thing that in communities like in Ronneby in Sweden, where exposure is high, you will see higher average serum cholesterol levels in the population. The toxicologists have been concerned about some confounding by enterohepatic circulation. Being an epidemiologist, all studies are confounded to some degree. I'm more relaxed about it, but there was also discussions about whether this was adverse or not, that you would have a few % increase in serum cholesterol. But I think most sort of public health medicine type of persons would say that this was not necessarily a desirable increase. Relating to the endocrine, what we have seen in some consistently in mice, developmental studies in mice, is that gestational exposure, very low gestational exposure, leads to altered structure in mammary gland development. So basically, you can see altered structures in the offspring in the mammary gland. And this is seen at doses which are really, really low compared to what you usually see in rodent studies. And this effect has been quite consistently reproduced. And this would generate any structural changes in the mammary gland would be of concern. And maybe the reason why this was not taken forward as the most critical outcome was simply because there was another endpoint that was considered more critical, which was the vaccination response, and the fact that both in humans and in rodents, you would see quite consistent reduced response, antibody response following vaccination in both animals and humans. And you would see this for several different types of vaccines, even though few have been studied in humans, and you would see this in very controlled circumstances in rodents, although depending on the design, the dose needed to actually produce this effect would be very, very different. And it was also considered that this effect, even though it's unspecific, these types of studies, they are actually testing the functionality of the immune system to respond. And therefore it was considered adverse. And just to sort of wrap up in terms of what this sort of health-based guidance value that was derived in the 2020 EFSA opinion means, it was derived in a way that the vaccination response would cover the other outcomes, including the endocrine outcome on mammary gland development. It was derived in such a way that we established a level based on a study in 1-year-old German children. We estimated where the concentrations of these 4 long-chain PFAS where no change in antibody response would be expected. And based on that internal level in the offspring, we would estimate what would the corresponding level in the mother be if she would have been breastfeeding her infant exclusively for 12 months. And that was around 7 nanograms per ml. So basically on that level, 7 nanograms per milliliter in blood, it was back calculated to intake, and that corresponds to around 8 nanograms per kilogram body weight per week, which you can consume as a woman of childbearing age without having the risk of your offspring having any adversity in relation to this vaccination response. But the levels that we need to get to see any association in vaccination type of studies would be considerably higher. So it should be quite protective. So in conclusion, PFAS are tricky substances. Some of them, particularly long-chain substances, have been extensively studied. They seem to act both on the liver and liver-related outcomes. There seems to be some endocrine-like properties. I would guess that this is quite unspecific and has something to do with their protein bindings and membrane bindings. There are limited or no toxicological information for hundreds of other substances. And I mean, although the bioaccumulation property can be predicted to some extent, it's still quite difficult, and it just makes it more difficult to study these non-persistent compounds and identify which effects that they have. But I think, at least for the long chains, that the current health-based guidance value should be protective. But I think this sort of history now, and now we are dealing with contaminated issues all around Europe, it reminds you really about what happened with the organochlorine compounds, where people were advertising that were, at the time in the 50s, and when they were marketed, they were the best things in sliced bread. And I think it was the same with these PFAS, but we are not really good at predicting neither toxicity nor bioaccumulated properties when we market new chemicals. Thank you.
Thank you, Thorhildur. We have a few questions. We have two questions. I think we have time for both of them now. There's a quick one. You mentioned what the Teflon. I think you mentioned quickly that the PFOA was burned off, and there's a question here from Anna Rakova. Did you say that Teflon pans are okay? Can you answer that quickly?
It depends on what you mean. What is okay? I mean, in theory, the PFOA or the technical agent used to produce the polymer is cooked off, or very rapidly cooked off. I'm not saying it's okay. If you think about environmental concerns, that's definitely not okay. So it depends what you look at. But I don't think you would find higher levels in humans that consistently use these type of polymer type of products. I think you would need to be in contact with the agent. But that is my understanding. But having said that, there is a lot of information out there.
Okay. And the next question is from Pricha. I don't know if I pronounced that correct, but the question is, does PFOA display the phenomenon of bioaccumulation, just like DDT, as it is fat soluble, and can it be stored in the body for a long time, or can it be removed from the body? Does transplacental transfer occur? That's three questions in one, but I'm sure you can answer them.
So the bioaccumulation is because of renal absorption. And as long as you don't separate the transporters, then it's more rapidly excreted if you get highly exposed for a short time. It is not fat soluble. It binds to protein, but the kidney recognizes this as a nutrient and recirculates it. The other thing, fetal, it crosses the placenta. These compounds cross the placenta to a varying degree. And yes, you can speed up. I think there are some studies showing that you can speed up the elimination of these compounds. And cholesterol-lowering drugs, which in fact the enterohepatic circulations have been used to do that. I think people who eat fiber-rich food would get rid of these compounds more rapidly because they bind, due to their absorption. But that's a little bit sort of gray area, I would say.
And is it correct that PFAS also have been found in breast milk? So in a way, it's a way of getting removed from the body, but then maybe entering your child. So
yeah, so especially the more water soluble, like the carboxylates, like PFOA, it is very rapidly excreted in breast milk. While PFOS, you can find it in breast milk, but the partition rate is slightly lower. Yes.
Well, thank you. And with that, we will move to the next presentation, which will be by Paulina Damdimopoulos. I used to say Damdimopoulos. You can say it yourself. But you are a research group leader at the Department of Clinical Science, Intervention and Technology at the Karolinska Institute in Stockholm. And your focus has been research has been focused on chemicals and there's mixtures associated with decreased fertility in women, and identification of mechanisms by which chemicals adversely affect the normal development and function of the ovaries. So please, the screen is yours, Paulina.
Thank you so much. And of course, thank you for the invite to present my results here today. So my name is Paulina Damdimopoulos, and I come from Stockholm, Sweden, where I work at Karolinska Institute. And the topic of my talk today is PFAS and other persistent chemicals in vital organs of unborn babies. So as Anna Maria mentioned, I work as a research group leader at Karolinska Institute. The name of my lab is Chemicals and Female Fertility. And the research in my group is focused on four main aims. Firstly, we are very keen to understand how chemical exposures look like in women living in Sweden and in their oocytes and their babies, and if these exposures associate any adverse outcomes. We would, of course, also like to know how these associations take place. So we would like to know the mechanisms underlying the adverse associations. And then we would like to develop tools to study such effects in vitro in order to recognize chemicals that might be toxic in women. And finally, we also work with fertility preservation in childhood cancer. But today I'm focusing only on the first aim, and specifically on our studies on chemical contaminants in human fetuses. The studies that I mentioned have been funded by the Swedish Research Council Formas and the Finnish Janne and Atus Erkko Foundation. And the stars of the show are really, I really have problems with my... Yes, so the stars of the show are Rochelle and Marie-Therese and Lynn, who are the researchers who carried out the studies, collected samples, and wrote the papers. So the presentation is basically a journal club based on 2 papers we've published, one in 2019 describing PFAS concentrations in human fetuses across the entire gestation, and the second paper has also information on lipophilic persistent organic pollutants in full-term human fetuses. How do we get the samples? We work with 2 different main sources. When it comes to the first trimester, we have samples from elective pregnancy terminations, and they represent gestational weeks 7 to 12. In our study, these samples came from Denmark. The trimesters 2 and 3, the samples are derived from intrauterine fetal death cases, and these represent gestational weeks 22 to 41. And as I mentioned, in the first study, we covered all 3 trimesters, and in the second study, we focused on the full-term fetuses that would be ready to be born.
Yes,
and
here's a question, Paulina. I'm still seeing your first slide. I don't know if that's only my problem.
Oh dear. I am moving forward, so I wouldn't know what's wrong.
Yeah. Now you put it.
What do you see now?
Now I see your slide 4, I think.
Okay, well, that's what I was
I hope
trying
it
to
will
show.
change. I hope it's not only me, but
Yeah, well, thank you. Yeah, just please, of course, tell me if something's not right. But right, so 2 studies, the first one on PFAS across the 3 trimesters of human gestation, and the second study focusing on the full-term babies. And in all these trimesters in the full cohort, about half of the fetuses were female and half were male. And now I try to change my slide. So we had focus on persistent chemicals, as you probably understood by now. PFAS, we had main focus on these 6 chemicals listed here, although as you heard, this is a family of thousands of different chemicals. And then we also measured about 20 organochlorine chemicals, flame retardants, PCBs, old pesticides that have been banned globally by the Stockholm Convention over 20 years ago. And then these PFAS chemicals, some of them have been added to the Stockholm Convention, and hopefully all the rest of them will be soon also regulated, at least in the EU. So if you look at the data from PFAS in human fetuses, I will start by showing a heat map about the frequency of detection of these chemicals in the samples. Here we have serum samples from the mother and placental tissue from the pregnancy by trimester 1, 2, 3. And on the top, you see the 6 different PFASs we measured. If the color is red, it means that every sample we had detectable or quantifiable levels of this chemical. So in the maternal serum, every woman in the study had PFOS, PFOA, and PFNA, and also most of the PFDA in their sample. And in the placentas, we see that PFOS was present already in the first trimester, nearly in all placentas, and the levels tended to increase as the pregnancy continued. If we now look at the fetal tissues, we had fetal liver, lung, heart, central nervous system, meaning brain or the spinal cord in the first trimester, and fetal adipose tissue that we could collect towards the end of the pregnancy in trimester 2 and 3. And you can see that it's not as red anymore, but we can still detect these chemicals in the fetal organs as well. For example, by trimester 3, all fetal livers contain PFOS and PFOA, and most of them also PFNA. Same goes for the lung and the heart, and even the adipose tissue. So we can conclude that fetuses are exposed to a mixture of PFAS chemicals through the whole pregnancy. And if we now look at the burden, how much of these chemicals we have, I've summarized here the 5 PFASs that we detected in the samples as cumulative charts by the organ. So trimester 1, most PFASs were in the lung, and trimester 2 and 3, we were mainly finding them in the liver and lung as well. And the central nervous system was always least exposed, meaning that the brain was a bit more protected than the rest of the organs. And PFOS and PFOA were the most commonly detected chemicals. We also looked at the accumulation by gestational week. We couldn't see a linear trend in the fetal organs, but we found a linear trend for PFAS accumulation in the placenta. And interestingly, we saw that in pregnancies with male fetus, the placentas tended to have slightly more PFASs than those where a female fetus was. So moving on to the organochlorine chemicals in term fetuses, I show you here the similar heat map as in the previous slide. And this time, it's not only the color, but also the size of the dots that matters. So the bigger the circle you have, for example, this big circle here means that the more samples had quantifiable levels of the chemical. So full circle means all the samples in the cohort had this chemical. And the more red the color is, the more of the chemical we found. So for example, this red color means that it was the highest concentration among these samples. In maternal serum, these lipophilic persistent organic pollutants that have been banned globally decades ago, we still see them. That's why they're called the legacy chemicals, because they are persistent, they bioaccumulate, and they are with us for a long time to come. So many of these pesticides are still there, and PCB chemicals. In Swedish samples, we typically don't find these PPDEs, flame retardants, because they were never used that extensively here. Placenta has a similar profile, but now as we move to the fetal tissues, we can see that actually the fetal adipose tissue has a very rich diversity of these chemicals, which we would never predict if we only looked at these typical maternal samples. So the pesticide DDT and its metabolite DDE is highly present in every sample, all the PCBs, and even some of these flame retardants that we would never guess are there if we only looked at the placenta. And this is, of course, because they are lipophilic. They will be probably present in the maternal adipose tissue and then mobilize to the fetus and deposit to the fetal tissues. Here we also looked at the accumulation by gestation, and we saw linear trends, not only for placenta, but also for some fetal tissues. So, for example, in fetal brain, we saw a trend for many of these chemicals where the longer the gestation had gone, the more of these chemicals we had in the brain of the fetus. I mentioned that the samples were from intrauterine fetal death cases, and a very common finding in stillborn babies is placental disruption. So basically placental insufficiency. And we were, of course, curious to see if the chemicals in the fetus might be somehow affected by the placental function. And when we compared fetuses with normal placentas in white and those with placentas that were insufficient here in black, we were able to see that there were more chemicals in the adipose, liver, heart, and brain of those fetuses that had a normally functioning placenta. I also told that half of the fetuses were boys and half were girls, and we looked at the impact of fetal sex. And here we saw that in black males, they tended to have more chemicals in placenta, heart, lung, and brain compared to the female fetuses. So as a summary, males with normal placentas had the highest levels of chemicals in their organs if compared to the female fetuses with insufficient placentas. Again, some of these fetuses were the same as in our PFAS study, so we were able to look at the whole burden of these persistent chemicals in the fetuses. And this now shows the trimester 3 situation in those cases where we had information on all chemicals present. In maternal samples, the serum and placenta, we found mainly the PFAS chemicals, here in orange colors. If we look at the fetus, we can suddenly see that especially the fetal fat, we have a lot of these organochlorine chemicals as well. And also in the liver, nearly half of the chemical burden is actually these organochlorine chemicals. And the brain is least exposed, suggesting that the blood-brain barrier is functional even during the fetal development. However, chemicals even make it across this barrier and can be found in the brains of fetuses. So what would I like you to take home from this presentation? So first of all, the chemicals I mentioned did not exist a century ago, so they are new and they are now ubiquitously contaminating the environment and biota, including humans globally. And that means that our babies are born with this legacy of uncontrolled use of chemicals by human society in their vital organs when they are born. And of course, these chemicals are not the only ones out there. We know that, for example, the European market has about 100,000 chemicals, and we know that the chemical industry is growing and new chemicals are introduced to the market continuously, meaning that the diversity and amount of chemicals we're exposed to is increasing. We saw in our study that the exposure of the fetuses was affected by the length of the gestation, the sex of the fetus, and also placental function. And we know that early life is a sensitive window of development to chemical insults, and therefore, when we assess the safety of chemicals, we should also consider the most vulnerable, which might be the unborn babies. However, if we try to estimate the chemical exposure in the baby based on the mother samples like serum or placenta, we might get false estimates of what is actually in the developing fetus. And the observations that the placental function and fetal sex affect the chemical exposures in the fetus suggest that when we do pregnancy cohort studies, those statistical models likely should be adjusted for multiple factors from the maternal that describe the maternal physiology and also placental function, so that we get more accurate estimates of associations between exposure and outcome. I also think that biobanks within healthcare should be more extensively utilized by toxicologists. The one that I got access to was perinatal pathology biobank, and I'm sure many hospitals have similar resources, and we would learn so much more about these important life stages that are otherwise almost impossible to study in humans. And I, of course, always say in the end that ideally we would have a society where industrial chemicals, human-made chemicals are thoroughly tested for safety and toxicity before they are taken into use and before they might end up being a legacy our unborn babies carry to next generations. Thank you.
Thank you, Paulina. I see no question in the question and answer, but I have a question for you. It was a striking sex differences in the levels seen in male versus female fetuses. And do you have any idea of the mechanism behind that difference?
I think this is why it's lovely to work in a hospital with many clinicians. So the obstetricians were not surprised at all. They say that the placentas work differently between boys and girls. Boys grow bigger, they need more blood flow and nutrients. So therefore the placenta is a bit more efficient when it comes to boys. And probably that also then brings more toxins or whatever is in the mother's blood to the male fetus.
Well,
so that's a theory.
Yeah. And makes it what your point with in your statistical data analysis to really consider the sex of the fetus as well.
We always say that cohorts findings are inconsistent, so we don't know, but I think we just don't know how to adjust these models properly so that we would really know what is in the fetus.
Well, thank you very much.
Thank you.
And now we will move to the next presentation, which will be by Inge van Bijsterveld, who is a medical doctor affiliated to the Department of Pediatrics at the Erasmus University Medical Center, Sophia Children's Hospital. And please, the screen is yours, Inge, if you can share your presentation.
Good afternoon. My name is Inge van Bijtveld. I'm a medical doctor and a postdoctoral researcher at the pediatric department of the Sophia Children's Hospital in Rotterdam, the Netherlands. And with this presentation, I want to tell you something about PFAS exposure in young children. As already has been said tonight, that PFAS are non-degradable man-made chemicals, and those are thought to have a wide range of adverse effects. In adults, they are thought to associated with cancer, thyroid disorders, and changes of plasma lipid concentrations. And in this presentation, I will merely focus on children. And in children, PFAS are thought to have a potential wide range of several developmental effects, such as the decreased vaccination response that already has been mentioned, but also growth restriction, increase of adiposity, endocrine disruption, and altered behavioral patterns. However, these are all based on small studies with multiple short follow-up and have conflicting results. And in fact, knowledge about the plasma PFAS levels in young children, especially in early life, that were lacking up until recently. So I want to show you the results of studies of our study group. And first aims were to evaluate longitudinal plasma PFAS levels in young children and to determine which maternal and infant characteristics were associated with these plasma levels. And these studies were conducted in the Sophia Pluto cohort, which is an ongoing prospective birth cohort study in Rotterdam, the Netherlands. And it's primarily focusing on growth and body composition in healthy young children. And all included children were full-term born, and they were included before they were 4 weeks old from maternity wards in the Rotterdam area. And they all had uncomplicated pregnancy and neonatal periods. And children were excluded if there was any congenital or intrauterine disease, asphyxia, or maternal disease or medication use that could interfere with growth and development. And in order to study the longitudinal plasma levels of these children, we included a subgroup of almost 370 healthy term-born infants of this cohort. And we collected detailed data of the mothers, of their pregnancy and deliveries, on the infant characteristics and also the infant feeding. And then we took blood samples from the children at ages 3 months and 2 years. And in these blood samples, we determined these 5 PFAS levels. And then we studied the associations of the mother and child characteristics with the plasma PFAS levels at age 3 months and 2 years. And these are some of the results we found. On the right side, you see for each individual PFAS the plasma levels on 3 months of age and 2 years of age, and then separate for the total group, where that's a black line, and separate for the children that were exclusively breastfed in the purple line, and exclusively formula fed in the pink line, and the green line were the children that had mixed feeding types. And what we found is that we could measure the PFAS in all plasma levels, of in all plasma samples, and that between the ages of 3 months and 2 years, the level slightly decreased of the PFOS, PFOA, and that the PFNA and PFDA remained stable during this time period. And as you can see in the graphs, is that we found that the PFAS levels were 2 to 3 times higher in the children that were exclusively breastfed compared to the children that were exclusively formula fed. And we also looked at which determinants were most important for the plasma PFAS levels. And at the age of 3 months, we found that especially having exclusively breastfeeding, being a firstborn, and a higher maternal age were important determinants for a higher PFAS level at age 3 months. And the most important determinants for the plasma PFAS levels at age 2 years were the plasma levels at age 3 months. So those were higher. The plasma levels at age 2 years were also likely to be higher. Also, a longer duration of breastfeeding was associated with higher plasma PFAS level at age 2 years and being Caucasian. So we found that the plasma PFAS levels only decreased slightly between age 3 months and 2 years and were highly correlated with each other. And this most likely is due to the long elimination half-life of the PFAS in the human body. We found higher PFAS levels in firstborn from older mothers, and this is also potentially due to the longer accumulation period in those mothers. And it shows that childbirth is a potentially PFAS elimination pathway for the mothers. And lastly, we found that PFAS levels in exclusively breastfed infants were 2 to 3 times higher compared to formula-fed infants. And this shows that human milk is also a potential exposure pathway for PFAS in young infants. So the conclusion of this study is that PFAS exposure pathways in early life of probably pregnancy and human milk. And as also was mentioned, the EFSA has a tolerable weekly intake of PFAS. The guidelines were changed in 2020 based on the decreased vaccination response. And earlier in infant formula, PFAS levels were reported to be low. And in human milk, they are probably transferred over the mammary epithelial membrane through protein binding and direct transport mechanisms. So babies can be exposed to PFAS through human milk. However, the exact longitudinal PFAS level in human milk and the daily PFAS intake through infant feeding and the associations with infant plasma levels were never thoroughly studied. So the aim of the second study that I want to present is to evaluate PFAS levels in formula feeding and in human milk longitudinally, and to study the daily PFAS intake through infant feeding and its most important determinants. And also to investigate the correlation between the daily PFAS intake and the plasma levels in the infants. So again, we used the children of the same birth cohort study, and the detailed data we collected about the mothers and also their diet, the pregnancy and delivery, the infants and the infant feeding. And we collected the samples of the blood. Again, the blood samples that used were those for 3 months and 2 years. And also we asked the mothers to collect a new human milk sample when the baby was 1 month and 3 months old. And then we measured the PFAS levels in the human milk samples we collected, in the blood samples, and in the 6 most used brand of infant formula. Then we calculated the daily PFAS intake based on the concentrations we found in the milk and the amount of feeding the child would drink. And then we studied the associations between the mother and infant characteristics and the correlation between the levels in the milk and the plasma levels we measured. And then we found that we could measure PFAS in the human milk samples we collected, but in the infant formula, the PFAS was not above the detection limit, so they could not be measured. And in the human milk, the levels of PFAS decreased slightly between the age of 1 month and 3 months. And in the graph, you see the levels of PFOA and PFOS on the upper row, and the daily intake we calculated on the lower row. And what you can see is that the daily intake is highest in the exclusively breastfed infants that are shown in the blue line, and lowest in the exclusively formula fed infants that are presented in the black line. We also looked at the determinants of the daily PFAS intake, and we found that the most important determinants were the amount of formula a day. There was a negative association, so the more formula the child received per day, the lower the PFAS daily intake was. We also found an association with the parity of the mothers of previous breastfeeding of another child, and if that was the case, then the daily PFAS intake was also lower. We also found an association with maternal age, and the higher the maternal age, the higher the daily PFAS intake was, we found. And we found that the daily PFAS intake was highly correlated with plasma PFAS levels we measured at age 3 months and at age 2 years. So we found higher daily PFAS intake in exclusively breastfed firstborns from older mothers. And this, we think, is again due to the potentially longer accumulation periods these moms had, so they could have more PFAS to excrete in their milk to their children. So also breastfeeding seems to be a potential PFAS elimination pathway for the mothers. And we found that daily PFAS intake at 3 months was highly correlated with plasma levels at 3 months and at 2 years of age. This is probably because of the long elimination half-life of the PFAS, and it shows that the early life exposure to PFAS probably has an impact throughout the whole infancy period. So the conclusion is that breastfeeding is an important exposure pathway in early life and has potentially lasting effects. And because of the potential harmful effects of PFAS, and especially during sustainable periods of life in which the development periods that are important for the development, such as the early life, it's important to know if there is effect of these PFAS at long term and what those effects are. And the first months of life is among other things an important period for adiposity programming, because studies have shown that especially accelerated weight gain in the first months of life leads to disproportional high fat mass and lower muscle mass in young adulthood, and that can lead to obesity, overweight, and diseases such as cardiovascular disease and diabetes. So what we aim to study is if there is an association between the PFAS levels in this critical window, so at the age of 3 months, and accelerated rise in fat mass percentage during the first 6 months of life. And we did that by the same children that were studied previously, but again, the PFAS measured in plasma samples at age 3 months. And then we measured fat mass percentage by p-POT and investigated if there was a rapid rise in fat mass percentage between birth and 6 months. And rapid rise was defined as more than 0.67 standard deviation scores, which is crossing one line in a growth chart. And what we found is that infants with a high PFOA and total PFAS levels at age 3 months had higher odds to have accelerated rise in fat mass percentage during this first 6 months of life. And because this is this critical window, and a rapid rise in fat mass percentage in this first period of life could lead to unfavorable body composition and metabolic outcome in young adulthood. So that the high PFAS levels in early life could influence this adiposity and could have an adverse effect later in life. So the conclusion we based on this is that higher plasma PFAS levels do associate with rapid rise in fat mass percentage in the first 6 months of life. And this could potentially lead to obesity and unfavorable body composition later in life. But longer term follow-up is warranted to see if there's indeed this effect. So in the future, we want to see those children again when they are older. So when they are 5 years old, and to measure their body composition and see if there's indeed an effect to adiposity or body composition from higher PFAS levels in early life. And I hope I have the results soon, in a couple of months. So this is what I wanted to tell you.
Thank you, Inge. And there's one question in the question and answer box, but I will save that for the general question. And I will just say for everybody listening that if you have questions for any of the speakers tonight, you are more than welcome to put them into the question and answer box that you will find at the bottom of your screen. I have one question for you, Inge. So breastfeeding, and the more you breastfeed seems to be associated with more exposure of your child. And we heard from Turhaldur before that one of the most sensitive endpoints that have been seen for exposure to perfluorinated compounds is also the immune response. So breastfeeding, we know in itself is beneficial for the immune response of the child. And PFAS in breast milk is probably doing the opposite. So I mean, should we stop breastfeeding because of the PF? And then, I mean, we don't have the beneficial effects of breastfeeding, or where do you think, what would your recommendation be?
So my recommendation would still be to continue breastfeeding because of the known health effects that have been thoroughly studied. And we did find that there were higher plasma concentrations of PFAS in children that were exclusively breastfed, but we don't know if those amounts do have adverse effects for these children. This is very important that we study that. And up to date, there are no scientific proof that the adverse effects outweigh the benefits of breastfeeding. So my recommendation is to keep breastfeeding.
And I think that also was the answer to the question put in by Anna Rakovac. I was also intrigued by some of the factors that you said that you found were associated with more higher PFAS levels, was being Caucasian, and did you have the opportunity to kind of tease out, could that be a social economical factor? Did you adjust for that, or could it be differences in diets between different cultures, or do you have any?
Yeah, we think it has to do with the diet, and we collected data on the diets of the bombs, but they were for short term. So we asked them, what did you eat this week? But we think it has if you are Caucasian or not Caucasian, you have different dietary habits that you do for your lifelong. So I think it's because of those differences in diets that we found this this determinant.
So that could be interesting to see what should we avoid and what should we maybe eat more of. Yes. And thank you very much, Inge. I think if we could get all the presenters online again, I would start with thanking all of you, and especially for presenting very clearly. And I think this is a really interesting topic. I might be biased, but so are you probably. But also for keeping the time. And that leaves us some time for questions. I have some questions. You're still welcome to put questions into the box if you have something. But I think we should start with the question by Pret Shah, which I'm not sure we can answer. Maybe Turhaldo can or somewhere for it. But the question is, pacifiers for infants also seem to contain PFAS. I don't know that study, but I take that as true. Any legislation to control the content of such products? I know that in the EU there are specific requirements for products for children, but I don't know if any of you can know more than I do.
No, I think it's the general food law. So I mean, I would think that there's a minimum requirement to get something accepted, and I think early infancy is taken into consideration. It's a different thing what we would like to see in our baby's products, of course, but yeah.
Yeah, I think that's how close we can get to that. I have a general question to all of you, because you have been looking at PFAS levels in humans, in babies, and in infants even, and also in other groups. And what are the trends that we see? Because some of these PFOA and PFAS we know have been regulated, especially PFAS over the last 10 years, but do we see levels going down, or are they still there because they are so persistent? So are we still bioaccumulating these compounds, or is there hope if we start banning them now, if now this new proposal goes through? Have any of you any data?
Yeah, in our cohort, we collected the blood samples of the children between 2012 and 2020, and we see that over time they slightly decrease.
Okay.
But slightly.
Yeah.
But
so there might be an effect of some of the regulation we have done already.
But at the same time, we are seeing studies coming from areas where there is suspected contamination, where you see levels that are quite high, and the probability of picking that up in sort of surveys which are conducted in certain areas is rather low. So it's being more diverse, I think, to some extent. We are finding more highly exposed people because we know where to look for, and at the same time, in the general population, levels are going down. And to reach the level where you don't see any high levels, you would need to understand better where are the risks and how to respond to that.
Yes, and that is the scary part, that we do now know that we have hotspots where they have been highly used. You mentioned how airplanes feels. It's been used in firefighting foams. So areas where we have had highly use of firefighting foams are today hotspots, I think, in many different countries.
Yeah, I could add that my own studies on the fetuses, that was just a very limited time period, so I can't comment on how it changes, but I think we all are very familiar with the regrettable substitution, and all the studies we showed today were based on about 5 or 6 different PFASs, and once these are phased out, I'm quite sure new ones will replace the same functions, and we don't even know what to look at. So I would argue that we need to have a better analytical toolkit to recognize all fluorinated compounds in samples to really know how the exposure actually changes.
And maybe that is why this new proposal from these 5 EU countries are so important, that the idea is to say they are all dangerous until proven otherwise. So kind of turning the need of evidence around. I was also, I think this is a question more to you, Paulina, because you showed these differences in PFASs, how much you found in placenta and in the fetus and in the mother. And sometimes you could see that you could not always, from what you found in the mother, say what would be in the placenta. But was a striking difference with PFOS and PFOA being very high levels, and some of the others, PFDA and PDNA, I think it was, being lower. Is that simply because the exposure is lower in Swedish women, or is it because some of these PFASs travel less efficient to the fetus and to placenta?
Right. So I think that I didn't show the data on the maternal serum levels. We of course measured that as well, and the pattern was very similar to what is expected. PFOS, I think, average 4 nanograms, and then followed by PFO and so forth. So I believe that the mothers had quite what we would call normal level of exposure these days. And I think PFOA was the one going more efficiently. If we started to make these relationships from maternal serum to what we find in the fetal organs, we were able to see that some of these compounds went over more efficiently. I think PFOA was the one going most. We couldn't really explain it with physicochemical properties. We were trying to look at simple values from databases. So I'm not quite sure why they behave differently. I also found it very interesting that we couldn't see this linear accumulation through pregnancy. Like we would assume that the fetus grows and the blood flows, so you would get more and more. So now I'm working more and more together with this fetal medicine specialist to understand how the blood flow into the fetus changes through the pregnancy. It's not constant, so it probably also relates to that, how the accumulation in the fetus looks like. But as a toxicologist, I feel I have so much to learn from the clinicians, and it's so important to get their interest for these environmental topics so that we can actually work together more efficiently to answer the human-specific questions.
I think that's a very important point, as you mentioned, that the gynecologists could easily tell you that boys have a bigger blood flow through placenta. I never thought about that either. So, and for you, Thorhallur, you show this data on altered structures in the mammary gland, and then you say, well, we saw that, but interest was more on the vaccination effects because that was the most sensitive. But do you think that some of the altered structures that you can see after exposure to PFOA, could that be related to risk of breast cancer, or would it be more related to risk of function of the breast? I think there is from a Danish study doing the burner cohort, they found that the higher levels the mothers had of PFAS, the shorter breastfeeding period, which might be good because they don't transfer to the child, but it could also be maybe effect on the breast development that they simply can't breastfeed as well. Or do you have any thoughts about that?
Yeah, the problem, I mean, it is what you could say, I mean, effects on the mammary gland, structural changes would be something that is taken very seriously because you really don't know where that may lead. So that's why this was something that was heavily considered. At the same time, it's quite difficult to study this in human setting. You would have to call in the mothers, well, knowing the maternal exposure, call in the teenage girls and do a medical image analysis. And that is something that is not many studies can do, and you have to justify. And that is maybe the reason why we don't know so much. There are some studies suggesting that there are indeed problems with initiation of breastfeeding and so on, but there are a lot of issues there. So it's a little bit of a gray area, but something that I think it would be good to get more information since it is picked up in animal assays. It would be good to work on it further there and then go to the human setting to know better what you're looking at. But I think binding to proteins and membranes is something that could lead to such an effect easily. Yeah.
I have a continued question, if I may.
Of course.
Of the breast cancer or mammary gland, all women in certain countries have to go through mammography to get regular scans. In Sweden, they start at the age of 40, which I know from personal experience. Is that data anything that has been used to look at, for example, PFAS and epithelial density?
No, that would be very relevant. It would be very relevant to look at, I think. Yeah.
Great. Now we have a new study.
Yeah. Well, I don't have any more questions. I don't know if you have any comments before we start or stop. There's not more questions in the question box. So unless you have any comments to finish this up, I would again thank all of you for being here today, especially our presenters, but also all of you who participated. And yes, by this, I just want to maybe point your attention to other upcoming ESE events and say thank you for today and goodbye.
Thank you very much.